Hello all and welcome back to this course on computer organization. So having looked at various assembly instructions, the idea of compiling, linking and so on, we are now in a position to actually get into the core of part 1 of this course, right? And what is that? It is basically the job of compiling a C program. Okay, so let's take a very simple example here. Okay, I have on the left you see the one file1.c, file_1.c, which contains the main. Okay, it has some variable z, and I say z equal to fn of 2 comma 4, and I have a global variable which I say is equal to z after it returns from that function, and that function fn has a function declaration on top, int fn of int comma int. Okay, the global variable is also initialized outside this main function as to a value of 5, right? Now what do you see on the right hand side, file_2.c, it has int fn, okay, int x comma int y. I say int z equal to 0 and z equal to x plus y, return z. Okay, this is a very simple elementary C program, right? So the idea of keeping it so simple is not to focus on the translating the complex C statements into assembly. That can be done in a step-by-step manner. Like earlier we wrote string length and multiplication by repeated addition and so on, right? But that's not the focus here. What we really want to focus on is a process of compiling this into a consistent object file. Okay, now before I again, sorry, one second. So before I jump into this whole process of compiling and all, let me remind you that the process of compiling is only this box inside here. When I say compile a C program, I am only talking about that intermediate box. So therefore you are going to take a pre-processed file and then compile it and generate an object file from it. What is an object file? It's basically a collection of assembly instructions or machine code for that representing that particular file and set of functions in that particular file, right? Finally the linking will happen, you will get an executable out of it. So we are not talking about compiling GCC file1.c, file2.c. No, that is going to do pre-processing, compiling and linking. I am talking only about compiling the C code in this second step here. Okay, so that is the context, and in that context we are looking at two different files, file_1.c, file_2.c. So the main idea, remember I discussed this quite elaborately in the last lecture. When I compile file_1.c and file_2.c, this file does not know even about the existence of that other file. Okay, so file1.c, which basically has the main function, right? In fact, even if you don't have the main here, there is no problem. The third step of compilation, right, rather second step after pre-processing, that compilation will not throw any error because the compiler does not expect the main. It is only the linker that actually expects the main to be present. But in any case, file1.c has a main and it has this function declaration, okay, int fn of int comma int, right? And in main, what have I said? I have basically said int z equal to 0 and z equal to fn of what, 2 comma 3 or something. Okay, I am just calling this with some fixed numbers for now, 2 comma 4. So let's keep it consistent with the slides, 2 comma 4, right? And this function here is int fn of int x comma int y, and I am saying int z equal to 0 again here, z equal to what is the function? I am doing x plus y, okay, x plus y and then return z. So this is the very simple elementary program that we are considering in two different files, and when I compile file1.c, I should not worry about what is in file2.c and vice versa. Okay. So what do we first of all observe here, right? So is the program consistent? Yeah, int z. Okay. So first of all we notice, okay, that there are a certain standard functionalities of C that are being exploited in this. Okay, let us see what they are. First of all, there is a local variable z in both main and fn. Okay, and fn, right? So this guy, it's a very interesting thing. It has exactly the same name and it exists in both functions. Okay. Then we also have what is known as function parameters. What are they? It's basically the x and y in fn, right? So these are function parameters. So every time you call this function, you could call it with different parameter values. In this case, main is calling it as fn of 2, 4, right? I could always call it as fn of 3, 5, 3, 7, whatever it is, it doesn't matter, right? But these values are being passed from a calling function to that function and you're going to manipulate something with it, right? The third thing is they're the body of the function, okay? Body of the function fn. This is doing some z equal to x plus y. I could replace this by any other functionality, z equal to x into y, x minus y, x power y, whatever it doesn't matter, right? There are many ways of doing this, and effectively the compiler has to insert the necessary assembly instructions so that all of this will compile and come out correctly, right? The fourth point that you notice is we are trying to return a value, an integer. We are trying to return an integer z from function fn. So the function is doing some calculations and then that value is being returned back to main. Okay, so that value has to carry over. So in some sense there is some state which is being passed from the function, the called function, to the calling function, and that state passing has to happen correctly, right? Apart from this, obviously though I have not explicitly written it here, there is also a global variable. Okay, so there is this global variable, which is this g underscore I what, where. Again, as a naming convention, if I call a global variable as x and a local variable as x, right, and then you use it like this somewhere in between your program, you will have no idea whether that's a global variable or not, and that's why global variables are best named as g underscore I to say that it's an integer, and then you give it some meaningful name from there, right? The moment you see g underscore I, you know, 1, it's a global variable, 2, it's an integer, right? So similarly, if you want to have a positive integer, you call it g underscore n, right? So there are some very nice naming conventions that you can follow for variables so that the program is very much readable and you understand what the variables are deep inside the program without having to come back and see on top whether it's a function parameter or a local variable or whatever it is, right? So these are the interesting things that we need to keep in mind, okay? So apart from this, what we also see, right, are the functions and function calls, okay? So when we actually want to go from a C program to assembly language, we need to answer the following questions. How are function calls in C translated to assembly? Yeah, it's very intuitive. You might argue that you have to use the call assembly instruction to do this. Of course, that is correct, but there is more to it. Okay, it's not just as simple as that. Then there are function parameters. We just saw that x comma y in fn, right? So you need to worry about how function parameters can be passed to the function. Now, this local variable z that we saw right out here in both main and fn is a very, very interesting feature, because it allows you, okay, to do something locally and just move on with it. You don't have to. So for example, imagine if I didn't have the concept of a local variable and I write int z equal to 0 here, and I am compiling file underscore 1.c, right? Now somewhere in file underscore 2.c I will have another local variable z, and these two names should not clash. It is impossible, right? Because in a typical actual product or a program, you will have thousands of files, hundreds of files. How can you keep track of what is where and keep track of everything local like that? It is impossible. So these local variables are a boon to a programmer, okay? And it is very beautiful. The naming is absolutely, you can use exactly the same name. The programmer does not have to worry about allocating space or destroying the variable, nothing, right? So in some sense, we need to also worry about what does it mean to say that local variables are stored on stack. I mean, some very loosely you would have heard this somewhere or the other, okay? At least you would have heard the term saying local variables go out of scope after the function is done, right? So when you enter, so this local variable z, right, in main will come to life the moment you enter main, and it will cease to exist the moment you leave main. Likewise, when you enter function, its local variable z comes to life. When you exit fn, that variable is gone, okay? So there is a scope of local variables that we need to figure out, right? And of course, how are global variables accessed, right? Now, function parameters, okay? Let's have a quick discussion on this one, right? Right, function parameter. Now, let's say that I have in some hypothetical world a C programming language that allows me to take at most 2 function parameters, only 2, okay, int x, int y, or it could be just function of int x or function of nothing. It does not take any function parameter. If I had only 2 variables that I could pass, I would easily allocate one of these registers in the microprocessor to actually do this function passing, right? See, what is the function parameter passing? You are taking a state from the calling function and sending it into the called function so that you perform some computation and then come back. So this state, assignment from the called function to the from the calling function to the called function can actually happen through registers if they are just handful in number. However, you know that function parameters can be technically infinite in number. Okay, you can have any number of function parameters. I just showed it with an example of 2, but there are cases when you can have 20, 30, 40 parameters also that can be passed to a function, and therefore it is not possible to do this through registers. You can't do this through registers because there are only a finite number of registers sitting in a microprocessor. Okay, so now what about scope? Scope of this local variable is actually a very desirable feature, like I just told you, because as a programmer I don't worry about allocating space to it, I don't worry about destroying it. On the other hand, if you wanted to deal with variable memory allocation and stuff, you need to use malloc and free. Now for malloc and free, the programmer or the designer needs to keep track of exactly how much memory was allocated and free the memory the moment you are done with it. Okay, so if you have a pointer pointing to a malloc address, right, malloc portion of memory, and this pointer goes out of scope, then you cannot even delete that memory. That will lead to a memory leak and it could crash your program. So malloc and free is to be used very specifically for dynamic memory allocation. But most of the time as a programmer, I don't want to worry about this, and that's the reason the scope of local variables, right, is very, very desirable. You want this feature. You want that local variable z to come to life the moment I enter that function and z to go away when I leave that function. Okay, that's the only way the same z can exist in main and that any other function. Okay, now given that I cannot send function parameters on registers, local variables, again I can't put them in registers because there are many, I can have any number of local variables and stuff like that. Where do I put these variables? Okay, where do I put these variables? Where do I store function parameters and local variables? Where do I store them? Now, of course, the answer is if not registers, you need some storage, it has to be memory. So the answer is of course going to be memory. Now, in which segment do I store it? There are 4 segments, right? Code segment, data segment, extra segment, stack segment. Now, obviously I cannot put it into the code segment because anything in the code segment is typically expected to be some sort of an opcode and stuff like that, which will get interpreted as an instruction to the microprocessor. Therefore, you cannot put it in the code segment. So my choice is really between data segment, extra segment and stack segment. Now let us look at this word scope a little bit. Okay, now I spoke about the scope of local variables, right? I spoke about the scope of this z, but what about this int x, int y also? These are also in some sense like local variables. When the function is called and you enter it, these variables x and y have meaning. The moment you are done and you are out of that function, these x and y is gone. So that is also, it has very similar scope as that of local variables. Okay, and therefore where I need to store these local variables or these variables with scope in a place in the memory where automatically when a new function is called, something should happen. Something should happen in that memory, right? And the scope can automatically get defined. Okay, so now you remember that when we wanted to do function calls, right? I told you, you do call and ret. Okay, you do call instruction. What does the call instruction do? You give function underscore address. Remember, you give an address that you want to say, you call, right? So this call instruction will load EIP, right? With it will actually, before this, it will push the current EIP, because when call fn address is being executed, EIP will auto increment to the next address of the next instruction, and therefore that you just push onto stack, and then you will load EIP with function address. This is what happens in a call. Now the operation of pushing something onto the stack is very interesting. Why? Because the moment you push something onto the stack pointer will decrement. Stack pointer will decrement in this case by 4, and therefore the moment you call a function, some implicit push is happening and something on the stack is now being set specific to that function. So it's an implicit thing. So therefore, in order to actually handle scope of local variables, it seems that the best location in memory is the stack segment. So there is, for example, when a function gets called, nothing happens on the data segment or extra segment. Once you go into that function, some data movement can happen, data processing can happen of these 2 segments. But implicitly there is no change in the data segment or extra segment that indicates that a function has been called. Whereas the moment you call a function, something changes in the stack segment, and that is why that is more suited to implement scope of local variables than data segment or extra segment. Okay. Now, how do I access local variables? I need to access local variables. Okay. So, therefore, we are going to say that all local variables function parameters are going to sit in the stack somewhere. We will see where exactly. Okay. Now, how do I access these local variables? Remember that when I want to do this kind of an operation x plus y, I am not doing a last in first out, you know. So, let us say for example x and y are sitting on stack, right. Let us say somewhere in my stack memory like this, I have x sitting here and y sitting here. Now, does this mean that I have to access this x and y only last in first out? That means my stack pointer is pointing here, right. That means can I access only x first and only after you pop x can you access y? No, I would like to access local variables in a random order, and I need to be able to do random access of local variables in the stack. Okay, and therefore what I need is ESP is not the best register to access local variables on the stack. Okay, it's not ideal. Ideal to access local variables. Okay. Then what do I use? Remember, I told you there was another register which was called the base pointer. EBP was specifically meant to allow random access from the stack. Okay. So, for example, I would want to be able to do instructions like this, comma, contents of EBP minus 4. Okay, I am accessing the data from the stack randomly using EBP. EBP by default is associated with the stack segment register, and therefore data will get accessed randomly from the stack and it will go into EAX. So, I want to be able to do such instructions, and therefore EBP is going to be used to access local variables. Okay. So, it will not just be EBP, it will be EBP plus n, EBP minus n kind of thing, right. And therefore, yeah. Now, here I have to just summarize in brief what is going to happen before we actually get into the translation. Okay. So, before a function is called, right. So, let us say I want to call this function fn, right. It will translate to some call of some address, right. But what about that int x int y that I actually call? For example, in this case, right, I want to translate this function call. Of course, the function that call will simply translate to CALL fn, some address, right. Now 2, 4 are parameters. So, once I call this function, I would have gone into the other function there. So, there I do not even have access to this 2, 4 and all that. Therefore, before you call that function, you have to push these parameters onto stack. Okay. So, in some sense, parameters are going to get accessed as EBP plus n. So, your EBP will be here somewhere pointing to some location on stack. Function parameters will be pushed onto stack before you make the call. Okay. Therefore, EBP plus n will be function parameters, EBP minus n will be local variables. Okay. Now, how do I return something from a function? Remember that when you return a value, you are not interested in returning arbitrary number of values. Okay. You are typically going to return one value. So, even in C, you can only do return 0 or return x, return a float, double. You can return different data types, but you can return only one single value. If you want to handle multiple return values, then you need to do this through double pointers. right? Or sorry, you need to do it through pointers. Only then will you be able to handle multiple return values, okay? So we'll come to this a little later, but since it is only one return value, we can assign a register to actually do this transfer from the called function to the calling function. Whatever value has to be returned, we'll put it in EAX register. For example, integers are going to be passed back through EAX register, right? And of course, global variables are going to be accessed by direct address, okay? Now, the key point here, as I told you, is we are going to apply these rules and translate the C program to assembly in both file1.c, file2.c without worrying, without even knowing about the existence of these two. Okay, it's the linker who actually takes care of putting all this together. So the compilation process is not even going to be aware of this, and that's why it is very important that we have this function declaration on top, int fn of int comma int, so that the compiler knows that there is a function like this which will be provided to the linker at a later stage. So the compiler need not worry about this, and that's why the declaration is a very important step in this whole compilation process. Okay. So now I am going to get into this whole process of compiling the C code. So what we will do is we will do our inline assembly idea, okay, where we were able to go from C to assembly, and suppose we were to write some inline code, what would we write? Okay, that's what we are basically doing here. For example, in main, okay, int z equal to 0. Int z actually has nothing that will translate to assembly instructions. It's z equal to 0 that is going to cause this thing, and therefore I will say move z comma 0. So the value 0 in decimal will be loaded into the variable z. Now what is z? That we will come to later. For now I am not going to get into that. Then what am I doing? I encounter z equal to function of 2 comma 4. Okay. Now I am going to just for now assume that I will push parameters from right to left. Technically you can, for now you can also push from left to right, but we'll see later why right to left is better than left to right. For now let's just go right to left. So I see function of 2 comma 4. So I will simply push 0x00 whatever 4. Then I'll again push 0x0002, right? And then I will call the function fn. Okay, this is basically the very naive and simple translation of this function call. Now remember that when I call this function, it's going to go into that program, it's going to finish execution, it's going to come back. Okay. Now this file, when it is being compiled, does not even know about the existence of file2.c where this actual function exists. Okay. But when you return from function, okay, and you come back from that function call, you know that the function is going to send the return value in EAX to you. That's why after the call fn, what we have is move z comma EAX, right? So you can see that here, right? You can see that here I have move z comma EAX, okay? This is the protocol that we have agreed on. Now EBX also could have been used, but we have just said the MSVC compiler just says okay, EAX is going to be used to do this return of integer values from the calling function, from the called function to the calling function. Okay. Now move g comma ival equal to 0. This is a global variable. So this global variables have to be accessed by direct address. Why? Because whether you call from main or you call from function or whatever it is, it's basically going to be the same variable. So the only way to do that is to access it by direct address. Okay. Now come to the function call function on the right. This is file2.c. Okay. Again I have an int z equal to 0. That will also translate to move z comma 0. Okay. Then I say z equal to x plus y. So how do I do this operation? Remember, I need to first move a variable x into a register, then perform the addition operation with y. Okay, so I first move x into EAX, right? This is EAX equal to x. Then this operation EAX will become equal to x plus y, because EAX is already initialized with x. This operation is what is going to store the local variable z, is going to put the result of EAX into this, right? So therefore this is what will do z equal to x plus y. So for example, if you didn't want to do z equal to x plus y and you just said return x plus y, okay, then all you need to do is keep the return value x plus y in EAX. These two statements will suffice. And then after that, you encounter the return z statement. What does that translate to? It translates to RET. Okay, return z. Basically, there are two things. One is return and other is z. That's the local variable z. So that is going to be already sitting in EAX. And therefore, that return z, I don't have to explicitly do anything. For example, here if I had used EBX, okay, and this was also EBX, right, then I say okay, z equal to EBX, then what would have happened? Z, the local variable z, will get the value x plus y, but when you return from this function, EAX will not have. In that case, you would have to say EAX equal to EBX. See, this is a very simple example where we can use EAX directly. So we are not having to do all this jugglery. Otherwise, you have to take that value in final value of z and put it into EAX before you return from that function. Okay, that is just hypothetically I am telling you this example here. So let's now take off all of this, right, and finally we are doing a RET, and that is what is going to enable us to go from this function fn back to where it was called from. That happens to be main in this case, right? So therefore, this is a very naive translation of the assembly code of in file1.c and file2.c, oblivious to each other. Okay.